So coming back to looking at our distribution and back to histograms. Histograms tell us a lot of information. And in this example, you can see where like a bin range was created for specific audit days, and then also the count of audit days that existed in a certain bin. And these obviously give us some kind of frequency measurement for each of those occurrences. Now, one of the things that we want to look at is the shape of these distributions. And we look at shapes in actually two measurements. We look at it in terms of skewness. And so skewness might be something that would be like this. Or a skewed distribution could also be in the opposite direction like this. And this is different, of course, than our regular bell-shaped curve, which is, like this. And of course, excuse me, I'm drawing with a mouse. Now, kurtosis is something different. Kurtosis is, you might have a distribution that is short and wide, and another distribution that might be tall and thin. And so these are measures of, this is a measure of kurtosis, and it'll kind of tell you the difference between data distributions in those sets. So if we look at these examples, and we ask what's the difference between A and B in terms of mean and kurtosis, well, we know when we look at A and B, so here's A, it's the light tan, and B is the dark blue. A is taller and skinnier than, actually it's just taller than curve B. Now the mean is actually the same. So when it comes to the mean, we would say that the mean between A and B is the same, but the kurtosis of A and B is different. Okay. So now when we look at something like C and D here, in actuality, the mean value may also be the same. It's quite possible that they might be similar. However, the mode is completely different. Here you'll have a mode on this end and a mode on this end, because this mode would be giving us an idea where the most frequent occurrence of the observations are, right? And the skewness was also different, right? One is skewed left and one is skewed right. Now, if you ever wanted to know how to test what's skewed left and what's skewed right, imagine that you had a skier at the top of a hill, and he was going to go down the gradual side of a slope. He's going to go, in this particular case for curve C, he's going to go from left to right. So C is skewed right. It's the direction of the hill. And D, the skier would go from right to left. And left is where the direction of the slope is there. And so that is skewed left, right? So that will be one way of determining the direction of skewness. All right. Now, in our lab exercises, you're going to have to learn to use, or we have some examples where you use the data analysis tool pack, and I have some examples on how to get this into your Excel. We're using the histogram a lot in our data analysis tool pack, but you can also use descriptive statistics, and here's a short step-by-step on how to use the descriptive statistics in the data analysis tool pack. Also, in the newer versions of Excel, there's options to be able to create a box and whisker plot, and it's in the statistical charts tool in Excel. So look to the lab to learn how to use those as well. Now we're going to talk a lot about regression models and other types of statistical models. And this is for inferential statistics. So statistical modeling is a great way to be able to understand the relationships between variables. And typically with regression, we're going to put some type of variable in and get a response out of it. So one example might be, let's say that we look at people that have high level of education or different levels of education, right? And then we also then look at their salaries over time. And what we might find out is that we have the input, which is their level of education, and then find out their career salaries over time and look to see if there is some kind of relationship between the two. And it might be that the more education that a person has, it increases the likeliness that they will have a higher level of or higher salary in the future. This can be used for hypothesis testing and forecasting. Keep in mind this is inferential statistics, and just because something is found to be significant in its inference, it doesn't mean that it is always the case. And this comes into play when we start taking a look at correlation versus regression. Now, in correlation circumstances, we're going to want to make sure that we start to take a look at what is actually an input versus an output variable. And I mentioned, one input might be something like education, but a lot of times people might plot some type of graph where they might have, let's say, somebody's weight versus their height. And traditionally, we do see relationships between height and width. However, and it might look something like this, and we might see that if somebody weighs more, it's higher. It correlates more with their height. So if they are tall, they're probably weighing more, and if they're shorter, they probably weigh less, right? But this isn't always the case. We do see varieties of humans where they may be heavier and short, or tall and lightweight. But the whole idea, this is more about correlation, because you don't put in somebody's weight and automatically it produces them to be taller, or you don't put in their height and it produces them to be heavier or lighter. So this is a correlational difference, where in regression models, we're looking for inferential, whether it be an input and some kind of output relationship. Now, another idea when it comes to regression models, and a lot of times we're going to look at regression models, actually we're going to look at them in terms of a Y value, and what does it mean in terms of an X value. But also that X value, it could be X1 plus X2 plus X3. So a simple regression model will just stop at X1. But a multiple regression model will look for inputs, or look for multiple inputs. So we'll have X1, X2, and X3, and this builds upon that particular regression model. So how do we develop these regression models? We can use scatter plots. There's a method, a lot of times people will refer to OLS, or ordinary least squares. And the result of these techniques is with some type of measurement that was taken from an input versus output, a best fit line might be drawn, and that minimizes the what's called the squared of the errors based between the inputs and the output. And typically you'll get some type of function that will represent this line, as I have made up here above, and that might represent this. And then you'll get some kind of R squared value that will give us an idea about how strong of a fit or how much variation is explained by that particular line. So this is one area of inferential statistics where we use regression models. Now, one of the aspects about regression models that's most common is all these variables are continuous numerical data. Now, as we get into other regression models, it may change that the data may not necessarily be numerical in value, but it could also be categorical in value.